Okay, hello everyone, and thank you for sticking around until the very end. My name is Coldea from Oxford University, and let me start by thanking the organizers for giving me the opportunity to be part of this great school that I enjoyed very much so far. It's my third time in Cargés. First time I came about 16 years ago when I was a postdoc, and then 4 years ago I was one of the co-organizers for a similar school. So the purpose of my talk is to provide an experimental point of view on Kitaev materials, to build up on the introduction to Kitaev physics that you've heard from Lucille this morning. And I will highlight the experimental opportunities to see really new physics associated with quantum frustration in these systems, but also the challenges faced experimentally. So for the purpose of this talk, I'll remind some of the key features of the theoretically proposed Kitaev model for the Honeycomb lattice, and then what are the key ingredients that we look for in materials to realize some of this physics. And I'm going to review experiments on a number of candidate materials that have been explored already so far, both by our groups and also several other groups. So I'll talk about the layered honeycomb materials, sodium iridate, ruthenium chloride, and also an isostructural material, lithium iridate. And also I'll talk about generalizations of the honeycomb, or the planar honeycomb structure to other threefold coordinated but fully three-dimensional structures where also theoretically one expects Kitaev quantum spin liquids in some regime, and I'll discuss experiments on a number of materials that suddenly realize the right bonding geometry. However, all of the materials that I'll describe are ordered magnetically. And I'll describe experimental measurements to try and observe experimental evidence that the Kitaev interaction is indeed the dominant interaction term in these materials, and what new features come about because of that. So as Lucille introduced this morning, the Kitaev model on the honeycomb lattice is a model of Ising exchanges on every single bond, but with the particular feature that there are three families of Ising exchanges associated with the three different types of bond orientations, such that at every vertex there's bonds of three different colors or three different Ising directions preferred that meet at each point. And this incompatibility between the Ising directions is really the origin of quantum frustration and extensive degeneracy in the problem. So Lucille explained that by mapping the spins to Majorana fermions, one can achieve an exact quantum solution of the quantum model, leading to static fluxes as also propagating Majorana fermions with nodes at the Dirac points, at the K points in the Brillouin zone. So from an experimental point of view, it's always helpful to have some intuitive understanding as to why a system with these types of interactions might lead to a quantum spin liquid ground state. And I'll just give here some intuitive explanation. So a mean field ground state of the Hamiltonian would correspond to having all the spins parallel and along one of the Ising directions, say along the Z direction. So the Hamiltonian I'm considering has Ising interactions that are ferromagnetic on every single bond. So this arrangement with ferromagnetic spins along the Z direction is one of the classical ground states of the system. So here I should emphasize that X, Y, Z are axes in a Cartesian coordinate frame. So imagine that there is a cube where you have the X, Y, Z axis like this, and you view it along the main diagonal. So that's the projection of these axes then onto a plane. They form 120 degrees. But really, these axes are all reciprocally orthogonal. So that's the best you can do on bonds like this, because you maximize the Ising exchange along this bond. The gray bonds actually carry zero energy, because the spins are aligned along the wrong direction. Now, let's imagine that we take one of these ferromagnetic dimers and we flip it. Okay? There's no energy cost in doing this because these still remain ferromagnetically aligned and these bonds carry zero energy. Essentially, we can pick any ferromagnetic dimer and flip it independently of anybody else. And this is the reason why we get an extensive degenerate manifold of ground states. And so fundamentally, the quantum spin liquid ground state is a large superposition of many dimer coverings where each product state of dimers actually only satisfies a third of the bonds. Right? So the fundamental feature that gives rise to this extensive degeneracy is the fact that the Ising axes are incompatible when they meet at a point. So we have this quantum frustration associated with this incompatibility. And just the very fact that we need strongly anisotropic interactions, as Lucille explained in her talk, means that spin-orbit coupling is essential. Because any anisotropy is a combined effect of crystal field interactions and spin-orbit coupling. Spins by themselves don't know about the lattice. It's only their orbital motion that samples the bond environment, and only that way, through the spin-orbit coupling, they can acquire knowledge about the lattice environment, so in an anisotropy direction. So how do we realize the key ingredients to have Ising interactions orthogonal and meeting in a Honeycomb arrangement like this? So let's start with reviewing the magnetic ground state of iridium 4+ ions, which is one of the class of ions that in materials that are candidates for Kitaev physics. So iridium 4+ has 5 electrons in the D shell. So in a free ion, these have spherical symmetry and all the orbitals are degenerate. I'm showing here the 1 electron orbitals. Now, once we put it in a crystal environment with octahedral coordination of oxygens, then the orbitals, these 5 orbitals, can be classified into orbitals that point in between the oxygens, and these form the group T2G, and the orbitals that point along the oxygens, there's 2 of them. So if we put all the 5 electrons here, then we still have an orbital degeneracy left. And you've heard from your solid state course that orbital degeneracy is in general unstable. The conventional mechanism, if we ignore spin-orbit coupling, is to look at local lattice distortions and imagine that this octahedron now elongates along the z-axis. Then the orbitals that can have a z-axis component become low energy compared to the dxy orbital, which is all in the xy plane. So if we put all our 5 electrons in here, we gain energy compared to the undistorted case. So this is the basis of Jahn-Teller effect, which tells us the orbital degeneracy is unstable and will be ultimately lifted by lattice distortions, which, even though they cost some energy due to lattice distortion, that's quadratic in the displacement, whereas the electronic energy gain is linear. However, a very different scenario can happen when we have very strong spin-orbit coupling that overwhelms this energy gain from Jahn-Teller distortions. So an iridium is an ion further down the periodic table where the spin-orbit coupling increases as you go down. The periodic table increases as the atomic number squared. So it's very large compared to 3D ions. So here, if we think in terms of seeing still a 1 electron picture, this 3-fold degeneracy is equivalent to an effective orbital angular momentum L equals to 1. And when the spin-orbit coupling is projected onto this lower manifold, it's written in this form, minus lambda Ls, where L is the effective orbital angular momentum here. This is the spin of the electron. And for lambda positive, we want L and S to line up. So in a J effective angular momentum, so the ground state would be a quadruplet, J3 halves. and the higher state will be effective J half. And if we put all our 5 electrons here, then essentially we have a hole in the J effective a half multiplet. And what's important here is that contrasting to this situation down here where there's an orbital singlet ground state, this is a spin-only moment. In here, the spin and the orbital part are strongly entangled with one another, in a sense that if we pick one of these two representatives of this Kramer's doublet, then spin up would correspond to a certain orbital and spin down to certain other orbitals. So the spin knows about the orbital motion of the electron. So how do we generate the requirement for having a dominant Ising exchange? So one scenario that was proposed by Giacchelli and Kaliulin way back considers the scenario in which we have 2 octahedra that are edge sharing and looks at the super exchange between the iridium, oxygen, iridium, and also going through this other path up here. In detail, this mechanism is actually quite subtle, but qualitatively, the fact that spin is strongly linked to the orbital means that there are very strong constraints as to what spin states can actually interact with one another. For example, the only active orbitals are these orbitals that are orthogonal to the plane of the iridium oxygen. So this is one iridium, that's one oxygen, that's iridium, that's the other oxygen. So the hopping from here to there has to occur here through the xz orbital and here through the yz orbital. So the same spin state has to hop, and so here. And there's a quantum destructive interference between these two paths, and this leads to a cancellation of the exchange to first order in the hopping. So the Heisenberg super exchange cancels in this configuration, and at higher order in exchange, what the next term that's allowed is an Ising interaction between the components perpendicular to the square plane of the bond. Okay. So you can now see that if we have another octahedron attached to this other bond here, and another one to this remaining bond here, one realizes 3 bond planes that are orthogonal. Okay? So if we have an Ising exchange that favors the z-axis here, the y-axis here, and the x-axis there, this is really the key requirement to have 3 orthogonal Ising directions meeting at a point. Okay? So also I'd like to emphasize that we expect to have dominant Kitaev interaction for the super exchange. However, the 5d orbitals are quite extended, and there's also a possibility of direct exchange between the 2 iridium sides, not involving the oxygen. And here the processes are quite different, and the most general symmetry allowed form for the Hamiltonian is actually diagonal in the special axes where x prime goes along the bond, z is orthogonal to the plane of the bond, and y is the other direction. There's no symmetry relating all of these 3, so in this coordinate system, the most general form for the exchange contains independent values for the xx prime, yy prime, and zz prime. However, most of the description are in the qubit axes, which are rotated 45 degrees with respect to these ones. And so in that case, when this matrix is rotated into the cubic frame, then off-diagonal terms come up here that are equal in magnitude. Okay? And these 2 terms become the same. So the most general form for the Hamiltonian, even in the case where this is exactly cubic with axes exactly 90 degrees and so on, not including real material effects such as trigonal squashing and so on. So in the most general high symmetry case, we expect to have the Kitaev term, a Heisenberg term, and also what's called the gamma term, which is a symmetric exchange between x and y couplings. So it turns out that all of the materials that we found experimentally so far contain a combination of these terms. Okay? There's no material that contains just the Kitaev term. These other terms are also present, and they help stabilize the magnetic order seen in all of these systems. So I'll start first by describing measurements on lithium iridate, which is has the structural framework is that of edge-shared octahedra, which form a honeycomb arrangement in one layer, and then the layers are stacked vertically. And the stacking chooses one direction in the plane and carries on like this. So, which means that there is a unique axis in the plane. We've broken the full threefold rotational symmetry, and the crystal structure is monoclinic. So here are heat capacity measurements to show that there is an anomaly associated with the phase transition, which actually has magnetic character. These are susceptibility measurements. And through muon spin rotation, it's also observed that there's a local field that develops as an order parameter below the heat capacity anomaly. These oscillations in the muon signal indicate that there is a net local field that's generated. So to find out more about the microscopic ordering, we do powder neutron diffraction, and that's, as Colin explained, neutron diffraction observes the magnetic periodicity of the order via the interference Bragg scattering. And this is the plot of the diffraction pattern. All of these strong peaks correspond to the crystal structure, neutron scattering from the nuclei. But down here, if we zoom out, there is a new peak that appears at low temperatures, and this is associated with magnetic ordering. And what was surprising when we did these experiments was that this magnetic wave vector, of course, we can only know the magnitude through these measurements. So we know the magnitude is located somewhere inside the Brillouin zone, but it's very different to the wave vector for commensurate ordering, as I will show later, for sodium iridate and also ruthenium chloride, where the ordering wave vector is at the midpoint of the zone boundary. So in order to make progress and really find out what the magnetic ground state is, there's many possibilities. The Q vector could be anywhere on a sphere, in principle, in three-dimensional space. So making progress actually required the development of new techniques to grow single crystals of these materials. And finally, this was achieved through a new method of vapor growth and condensation under thermal equilibrium. You see here some crystals forming at the edge here. And these are the samples that we've investigated experimentally. And there was a lot of interaction back and forth between us doing structural studies and the scientists who grew the materials in order to refine the growth technique and improve the single crystal quality. And what I want to emphasize here is that so this is a honeycomb layer, and this is a hexagonal layer that provides the bonding. So in terms of the bonding between this layer and that layer, there are actually three possibilities for the honeycomb center. It could sit there, there, and there. And in terms of the bonding with the layer above and below, the energy is exactly the same. It's only the interaction energy with the second layer which makes a difference if these are in register or not, which means that energetically, there's a very low cost to have stacking faults, random shifts of the center from here to there, and so on. And this diffraction pattern here illustrates that on a sample which has essentially no correlation between the layers, instead of Bragg peaks, we see very extended diffuse scattering along the disordered direction. So you can see this lower trace out here. However, if the growth conditions are improved, then this has a massive change into these very sharp peaks that we see here. So this is a high-quality sample which is untwinned. Also, these materials suffer from the fact that they're almost close to threefold symmetry, so then many twins form, and here is a sample which had 3 twins rotated 120 degrees, which gave rise to all of these extra peaks here. So it was only through very careful selection of crystals that we were able to tell that the crystal structure is not actually threefold symmetric with a trigonal space group, but is monoclinic. And in the end, the crystals that come out, are still quite small, about 100 microns, or still sometimes a bit bigger. But really, they're not suitable for neutron diffraction. So what I'm going to show next is how we use X-rays, in particular resonant X-rays, to probe magnetic ordering. This is a technique that hasn't been yet described as part of this course. So the way one can think about conventional charge X-rays is that the incident beam has an oscillating electric field, and that starts to oscillate the electron cloud around the ions. That creates a polarization, and that radiates the electric field of the scattered beam. Okay? So the scattering amplitude is proportional to the number of electrons. And this type of process can occur independent of the incident X-ray energy. Okay? And for example, if the electric field is perpendicular to the scattering plane, it will emerge exactly in the same orientation in the scattered beam. So so-called sigma-sigma scattering. However, a new type of process can occur if the incident photon energy is tuned to what's called an absorption edge. So this is the energy required to take a core electron to the available states in the atom. So for example, here, the unfilled electronic shell is the 5D shell here. And so if the X-ray energy is tuned exactly to match the energy difference between a core level, such as 2p here, to this level, then the incident photon is absorbed. An electron is promoted up here, leaving a core hole. This is an unstable state long term, so the electron and the hole will recombine and re-emit the photon. So from the point of view of the photon, what's happened, we have a process photon in, photon out. And if this process is coherent across the sample, we can get interference scattering. But now, this is Bragg scattering, but this is now governed by an atomic scattering function, which depends on the particular quantum state that this electron has visited up here. And if we have magnetic ordering, it means that the electrons in this level have a certain spin orientation. And so imagine that there is one electron here with spin down. Then out of the two electrons that we have here, we can only take the one with spin up because of the Pauli principle. And so it turns out that the atomic scattering function gets modified, and in this case is proportional to the relative orientations of the incident polarization, the scattered polarization, and the magnetic moment of the electrons in this excited state. So essentially, the photon scatters by virtually visiting the excited state. And in this case, we can see magnetic Bragg peaks once there is a periodic magnetic ordering, because then the objects that scatter, these F, which are now vectors, have a certain periodicity. So we see interference scattering from this. And the relevant transition for Iridium to go to the 5D shell is to start from the 2p shell, and there are several levels, and I'm going to talk about transitions from a particular one, which has a very strong resonant enhancement. So the advantages of using magnetic resonant X-rays in this context are that we can look at very small crystals. So we've done experiments, extremely quantitative, very complex magnetic structures on 17 micron diameter single crystals. This is essentially just a speck into a powder. Okay? But because the X-ray beams can be focused to a very small diameter, and there are techniques to create extremely powerful beams, this size is perfectly fine to obtain very quantitative data. In fact, due to the fact that the beam is very intense, it creates a beam heating effect. So we have to attenuate the beam sometimes to 1% or 0.1%, and do these experiments because the beam is too strong. This will be totally inconceivable with neutrons to go to 1/100th of your incident flux. So also another advantage of this technique is that there's no magnetic form factor dependence. So we can access magnetic Bragg peaks at very large Q vectors, such as with index 24, which would be totally inconceivable with neutron scattering. So that gives us access to a wide range of reciprocal space to look at magnetic Bragg peaks. And in this particular context, neutron diffraction is not feasible given the sample size and also the fact that iridium is very strongly absorbing. So the experiments we performed were at the diamond synchrotron, where the electrons are accelerated and then they have their rotate in the storage ring very close to the speed of light. And then every so often in the storage ring, there is what's called an insertion device, which has little magnets that oscillate between north and south, over a distance of centimeters. And so that makes the electron beam wiggle very rapidly in space. And then when charged particles are accelerated, they radiate photons. And that's the process by which we can get very intense photon beams. So, so we knew already from neutron diffraction that the Q vector can be somewhere on a sphere with a certain magnitude. So when we go to the X-ray diffractometer and tune the X-ray energy to the right edge, and we do scans in reciprocal space, we find indeed magnetic Bragg peaks that are associated with the same wave vector. And these magnetic Bragg peaks occur at satellite positions around structural peaks. I'm showing them both here. The structural scattering is scaled down just to put the intensity to make it visible. So even though there's like 4 orders of magnitude difference, we can still see it. And the bottom graph here indicates that the blue trace is now sitting on one of these magnetic Bragg peaks and scanning the energy. So you see away from resonance, there's no peak. Essentially, this goes down to 0, and we see a magnetic Bragg peak only at resonance. And in contrast to this, charge scattering, which is one of these peaks, occurs at any wavelength, any energy, and in fact has a dip right at resonance, because there a large part of the incident beam is absorbed. Okay? So this very contrasting behavior enables us to test, to say what's magnetic and what's structural. So now that we know that the magnetic wave vector is incommensurate to the lattice, the question is, what is the actual structure? It could be a spin density wave that has that propagation wave vector, or it could be a combination of spin density waves. If there are 2 spin density waves that are 90 degrees out of phase, so when one is large, the other one is small, that would correspond to a moment of rotation. Okay? And even more complex situations can come up, as I'll explain shortly, when spins are actually counter-rotating on different sides. So for a propagation vector this way, we still have a mirror plane in the crystal structure that preserves the propagation vector. So this allows us to construct basis vectors for symmetry allowed elemental combinations of the phase factors between the 2 sides. So as has been discussed many times in part of this lecture, there are 2 sites of the honeycomb lattice, which I'm going to call 1 and 2. And the basic combinations are ferromagnetic and antiferromagnetic. So the spins are parallel or anti-parallel between these 2 sites. And there are different selection rules associated with being in phase and out of phase. For example, in phase would give rise to a large Bragg peak at the gamma point, whereas if they're in antiphase, there will be a cancellation right at the gamma point. But there will be Bragg peaks in other places in the Brillouin zone. And one way to think about the incommensurate ordering is to start with the spins in the commensurate arrangement, say ferromagnetic, and then introduce a phase between them. Okay? And that phase then is associated with the propagation vector. So if the propagation vector is 0, we start here, and then if we introduce a phase between consecutive sides, then these Q Bragg peaks move away. Okay? Yeah, so here is not the case because both of these structures have the same unit cell. So the crystallographic unit cell, the unit cell for ferromagnetic ordering, and the unit cell for antiferromagnetic ordering only require 2 sites in the unit cell, these 2. So we have 2 sites because of lattice periodicity. It happens here that they have parallel spin. We have 2 sites here because of lattice periodicity, and here it happens they're antiparallel. But I don't need more sites. 2 is enough. And then interference scattering between these 2 leads to, for ferromagnetic ordering, leads to intensity at every reciprocal lattice point, whereas for antiferromagnetic one, we have a pattern of 6, and we miss the one in the center, and then imagine translating this, so you miss out every other one. The Brillouin zone is the dotted one, that's right. Yeah. So experimentally, we look at several Brillouin zone centers, and what we find is that Bragg peaks occur both around peaks that are just F character, if you like, and also around peaks that are FA. So our task would be to identify whether these ones correspond to the same magnetic moments as these ones, or really they correspond to the A vector, or a combination of the 2. So, So for this, we exploit the polarization dependence of the scattering. As I mentioned before, the intensity depends on some combination of the polarizations of the incident and scattered beam and the magnetic moment. And in general, this will be a structure factor which has contributions from all the magnetic sites in the unit cell. And in the particular experimental configuration that we employed, with incident polarization orthogonal to the scattered beam, it's only the projection of the magnetic moments on the final wave vector that matters. So what we do experimentally is imagine the scattering geometry here, incident beam coming this way, scattered beam that way. So the scattering wave vector is bisecting the direction of these 2. So imagine now that we rotate the crystal around Q. Okay? So basically, if these are the periodic planes, we rotate them compared to incident beam coming this way and scattering that way. So normally, nothing should happen. For charge scattering, nothing happens. However, here, as we rotate the crystal, we rotate the direction of the magnetic moments rigidly. So we vary the projection of the magnetic moments onto the scattering wave vector K prime. And so if we sit at one of these points and do one of these so-called azimuthal scans, what we see experimentally is that the intensity has a periodic arrangement with 0 in the center and maximas at plus minus 90 degrees. And that's exactly what you expect to find if the magnetic moment here was orthogonal to the scattering plane, and here it had a large component along K prime, then it was 0 again, and then again it had a large component. So from this scan up here, we can uniquely identify that this magnetic Bragg peak is associated with so-called Fy, so magnetic moments along the y direction. So if we now look at these other positions, we find very different behavior. So first of all, these 2 satellites are, when one is strong, the other one is weak, and vice versa. And the behavior is really not symmetric around the full. We need the full 360 to get back to where we started. And this is a characteristic signature that we have an interference of scattering from 2 different basis vectors. If it was a single basis vector, the behavior would be symmetric. And also would be the same between the plus Q and minus Q satellites. So this interference means that the intensity depends on the intensity if we just had moments along the y direction, just had moments along the z direction, and here is the interference if we have them both together. And if the phase is 90 degrees, then this interference term actually changes sign between these 2. So that leads to this antiphase behavior. And as I mentioned before, when we have 2 spin density waves that are 90 degree out of phase, that's associated with a moment rotation. And because we have I'm just considering here one plane, x and y. So here, between x and y, if the vertical component is always parallel and the horizontal component is always anti-parallel, it means that they counter-rotate. Looking now at the full crystal structure, it means that if we take these two spins, if we now move in the neighboring unit cell this way, the first one rotates this way, and the second one rotates the opposite way. And this is very unusual because if one was to have Heisenberg exchange interactions between spins, counter-rotation means that one component is always in phase, one is antiphase. The energy is exactly zero once you look at the average it over the whole lattice. And I'll explain later that this can be naturally explained by a Kitaev interaction which favors these directions x and y on the different bonds. So one can realize on the honeycomb lattice many types of incommensurate phases. For example, if we just have if we consider second neighbor and third neighbor, J2 and J3, quite a complex phase diagram comes up. The nail phase is up here, which corresponds to the origin of this coordinate system, where we have anti-parallel arrangement between spins. And then various other zigzag and stripy patterns can be stabilized for strong J2 and J3. And there are three types of incommensurate phases that you can think about: spins being in parallel on the two sides, and then rotating together, or being anti-parallel and rotating together, or rotating vertically. But all of them are co-rotating between the two sides. And this counter-rotation is really a very robust experimental feature. There's really no assumption in doing the analysis. It just straight comes out from this interference term. And I'm illustrating here, in the case of co-rotation, the curves will be symmetric in azimuth and also symmetric between the two sides. So that's really incompatible with the experiments. So what I'd like to show next is some other generalizations of this lattice to other threefold coordinated geometries, which are possible in the case of lithium, because lithium and iridium have very similar ionic radii. So you can imagine that some iridium can occupy these positions in between the layers. And one way to think about what types of crystal structures can form is to imagine that we're looking at the honeycomb layers head-on. So the solid ones corresponds to the layer that's closest to us, and the dashed one is just behind. So imagine that you had a pair of magic scissors and you cut every other bond. And now you pick one of these honeycomb ribbons rigidly and pivot along these points and rotate such that this connection is then made with the layer behind. Okay? So this honeycomb ribbon was in this plane now, and you've rotated it such that it connects with the layer behind it. And this then leads to an arrangement where the honeycomb ribbons alternate like this. So it doubles the unit cell this way and leads to a different crystal structure. And this way, you can imagine that you can do other tricks. You can cut every single vertical bond, and then you have zigzag chains, and then you can connect those. And this leads to a so-called hyper-honeycomb structure, and this is stripy honeycomb, and there's other generalizations as well. So all of these structures have in common that every vertex is threefold coordinated. What's even more remarkable is that the Kitaev model that you've heard from Lucille solved on a honeycomb lattice can be solved exactly on all of this family of three-dimensional crystal structures using exactly the same techniques. All of them have quantum spin liquid states. They're now in 3 dimensions, so there have been new features such as finite temperature phase transition, and nodal points in the 2D now transform into nodal lines. Okay, so experimentally, it's possible to synthesize a lithium iridate also in 2 of these other polytypes. And here is the hyper-honeycomb, so zigzag chains, and here is the so-called stripy honeycomb, what we call alternating honeycomb ribbons. And we've done experiments on both of these. They can be synthesized in single crystals. and I'm going to show just experiments on one of them. So this also orders magnetically. As you see, there are signatures in susceptibility indicating an anomaly here. And doing the same type of resonant X-ray experiments, we also observe incommensurate magnetic bright peaks here that come out as satellites, and they have all the features of magnetic scattering. Here, the crystal structure is sort of includes more sites, so somewhat more complicated to deal with all the basic vectors, but the principle is exactly the same. So what we find is essentially the same type of counter-rotating structure that propagates along these zigzag chains. Here is an animation to sort of visualize this counter-rotating sense. And this is obtained by changing a global phase. Whenever there is an incommensurate structure, there's a global phase where you choose the phase of the origin. Okay? So this counter-rotation, as I mentioned, is very unusual and is not favored by Heisenberg exchange. It can be seen in other materials, and it has been seen, but it's generally counter-rotation that involves an energy cost on the lowest energy bond in the system. For example, this is a system of triangular layers that are somewhat distorted. So instead of the 120-degree structure, you have some spiral order where theta is slightly different than 120 degrees. But in each layer, spins co-rotate. They have to counter-rotate between layers because of the so-called Janoshinsky-Murray interaction that alternates between layers. But it's really just this weak interlayer bond that suffers because of counter-rotation. This is very unnatural for Heisenberg systems. And so what I want to give you a flavor of is to appreciate that this counter-rotation comes very natural in the case of Kitaev interactions. So if we just take one chain out of this magnetic structure, if you look very carefully, say if we label the bond slanted this way with X, if you now look at this pair of spins, they both have a component along X that's ferromagnetic. If we look here, they both have a component along X that's ferromagnetic. Here as well. Here along X, here along X, here along X, that's ferromagnetic. Now if we look at the bonds this way, Y, you see that these two spins have a component this way. These two spins have a parallel component that way, this as well. Yeah? So this is favored by the Kitaev interaction. So imagine that we have a Kitaev exchange on the zigzag chain. So the best you can do is to put ferromagnetic dimers. And then you have a choice how you put it between neighboring dimers. And so if we have a small antiferromagnetic exchange, then we make this dimer anti-parallel to the first one. And so the structure alternates like this. Now, this is not what we see experimentally. Experimentally, we see some rotation that breaks this collinearity between the spins. And one way to do that is to add a second neighbor coupling that breaks this collinear orientation here. And so this is the key thing. So imagine that you've added an interaction that wants these two spins to be away from exactly antiparallel. So let's say this spin has rotated clockwise, this way. So let's look at this spin up here. This will also rotate, and it has two choices. It can go to the left or it can go to the right. And in terms of the Ising interaction for this bond, it doesn't really make a difference if it goes to the left or right. But in terms of the interaction with this spin up here, which has already chosen to go that way, then if the spin goes in the opposite direction, then it will gain energy from the Kitaev interaction this way. And so these two spins counter-rotate. And when this is propagated along the same chain, this leads to this type of co-rotating spiral with opposite wave vectors on the two sublattices. Sorry, So the minimal energy is achieved when all of the spins move together somehow. Okay, maybe that's easier to show in this diagram up here. So, so if I just take these 3 spins, and this is the dominant interaction, that's antiferromagnetic. Now, if there's some interaction this way, they lose some energy if they tilt this way, but that's to second order in this coupling, and they gain energy to linear order in this coupling. Now, the question is, what does this do once these are tilted? And so the orientation of this is then chosen to have the same relative angles with these 2 spins as these other ones had. So the whole structure is characterized by, it's periodic, and is characterized by a rotation of spins as you move between unit cells. Oops, what have I done? Okay. So the zigzag chain is, of course, a cartoon, but one can generalize this picture to the full 3-dimensional lattice and use this so-called JK Kitaev model, and that produces a very complex phase diagram, but some of the key features seen experimentally with this counter rotation and so on are really explained by this minimal model. So what this shows is that the Kitaev interaction is the dominant exchange and does lead to magnetic structures that otherwise you cannot stabilize. So knowing the magnetic structure also gives us some insight into the magnetic excitations. And what I showed you, this animation of changing the global phase, we expect that to be visible in a gapless mode that comes all the way down to low energies. And indeed, we see evidence for magnetic scattering going down to the lowest energies that we probe. And we associate that with this Goldstone mode of changing the global phase. And then inelastically, we also see an onset of evidence for a gap mode, also above the Bragg peak position. And that possibly could be associated with fluctuations of the spins out of the rotation plane. And here are some pulse field measurements indicating that there is a transition at very high fields, about 25 Tesla. And interestingly, this Zeeman energy of this field matches the energy of this gap mode. So potentially, the mechanism of suppressing the order is associated with suppressing this gap. So how am I doing for time? 10 minutes, okay, fine. So briefly, I'd like to mention also some key experiments done on sodium iridate, which give evidence for Kitaev interactions in this material. So through a combination of thermodynamic and also resonant X-rays, magnetic neutron diffraction, and also inelastic neutron scattering, it's been possible to uniquely converge on the magnetic order, which has this zigzag form in this material. So spins form ferromagnetic zigzag chains that alternate in orientation as we go vertically along the honeycomb structure. And various DFT calculations suggest that, in fact, this can be stabilized, but only if one includes a number of terms in the Hamiltonian. So Kitaev term, but also Heisenberg interaction on the first neighbor J1, and also J3 is very important in stabilizing this kind of zigzag order. You see, it will favor this bond. This is J3. So how do we experimentally find information that Kitaev is present? Because this is a very large phase space. So in principle, if we just had a single layer, then one expects to find 3 zigzags. One that's has the propagation vector vertically, and then the other 2 rotated 120 degrees. Now, experimentally, it's observed that there's a single zigzag in a single crystal with a monoclinic structure. And that's because this threefold symmetry is broken by the monoclinic stacking of the layers. And then it's possible also to find the moment orientation, and you see that for the zigzag that propagates vertically, the moments are bisecting the cubic axes x and y. Okay? So this Bragg peak here is expected to have polarization xy, and so this one. Now imagine the situation that we did have threefold symmetry, and then there will be another zigzag that's oriented this way, so there'll be Bragg peaks here, but they would have different polarization, Y and Z, and so on. So this would be the position with Bragg peaks with these polarizations if we propagated in this zigzag, and the last figure would be if we had this other zigzag. So it turns out that this regime can be realized experimentally just above the magnetic ordering transition, because in that case, the system fluctuates, hasn't yet decided the order, and then if the monoclinic breaking of symmetry is rather weak, then the system would fluctuate between the three zigzags. Ultimately, if we go through Tn, it will pick one of them, and it will have Bragg peaks here. But if we're in a regime just above Tn, then it can fluctuate between all three. And here are some measurements of diffuse scattering, looking at the fluctuating spins that sample all these three zigzags from B.J. Kim's group. And then what's interesting is that the fluctuations are, the polarization of the fluctuation is linked to the moment direction. So for example, the Z spin directions would be expected to fluctuate at these two positions and also these two positions, but not at the vertical positions. And indeed, as ZZ scattering has Bragg peaks here and there, has spots, intense spots that are finite in momentum at these positions and not at those ones. And the other polarizations are also obtained by rotation. So this is a feature that very directly illustrates the momentum and spin locking. So spin fluctuation along a certain direction is linked with the moment. So this could never happen in a Heisenberg system where the system would fluctuate between all of these three with no polarization dependence. So there will be spots everywhere with 120-degree symmetry. So briefly about ruthenium chloride. So this has the same crystal structure at high temperatures as the two materials that I've described. So honeycomb layers stacked with an offset. And at low temperatures, it orders in a zigzag magnetic fashion, as one can find out from neutron diffraction measurements. And in samples that are very high purity, single crystals with no stacking faults, there's a further structural transition to a more high symmetry structure with sort of rhombohedral symmetry, but where still the in-plane structure is zigzag, but more complex pattern in between the layers. So here there are measurements, I'm showing measurements done of the phase diagram in applied field. There's very strong anisotropy between field applied in the plane and orthogonal to the plane. So here are measurements that we've done on a stack of ruthenium chloride sheets to observe that there's a suppression of the magnetic order visible via an anomaly in susceptibility around about 8 Tesla, and there's no further anomaly above that. And here magnetization measurements to indicate again this anomaly, which goes away at high temperatures. So what's important to appreciate here is that 8 Tesla is still a field that's way below saturation, in a sense that here magnetization measurements done in pulse fields up to 60 Tesla, and the magnetization is still increasing. Of course, only asymptotically, as you expect in a system with a non-conserved spin, but still from 8 Tesla to this, there's a wide regime to continue to quench quantum fluctuations. So the region immediately above the transition still has a large moment available to quantum fluctuate that's not ordered. So this has been refined in further diffraction measurements and also using other thermodynamic probes to show that, so here neutron diffraction, to show clearly that the zigzag magnetic Bragg peaks disappear around this kind of field. And here are AC susceptibility measurements which observe a fine detail that there's potentially another phase here that was already seen maybe in this drop here, associated with some change in the pattern between the layers, but still zigzag order in the plane. And the question is, what is really happening in this phase immediately above, suppressing the long-range magnetic order? Whether really it's a topological quantum spin liquid or a more conventional quantum paramagnet. And there are certainly some very interesting measurements in elastic neutron scattering which show that the scattering, there's a very strong signal at the gamma point in the form of a continuum scattering. So I just want to discuss some qualitative way to think about this physics and discuss some of the scenarios that are currently explored both theoretically and experimentally to understand the physics in ruthenium chloride, which has been explored in terms of excitations the most compared to all the other materials. So the agreement in the community is that the system is indeed very close to a Kitaev quantum spin liquid in a sense that it has dominant Kitaev interactions. But there are other terms, you know, J3, J1, gamma, these are present, and these stabilize the zigzag order. And as Lucille explained in her lectures, the Kitaev spin liquid is stable to perturbations. So we need some finite perturbation to take the system away from the quantum spin liquid. And then one would expect generically that there is some phase transition boundary, the solid line indicates Tn, that would go to higher temperatures as the perturbation increases. And so the material is believed to be located then somewhere close to this point. And so in temperature, then one would enter the zigzag order ultimately. And the question is whether these finite temperatures or higher energies in terms of inelastic spectrum, one can still observe some of the physics that's characteristic of this point up here. Now, turning to measurements in applied magnetic field. So again, so now imagine now that you put the magnetic field along this axis. So I'm just going to show then this plane. So this is the perturbation that takes us away from the Kitaev spin liquid, stable up to this point. And now we apply a magnetic field along a direction that, as Lucille explained, one has to have components along all three directions to get a gapped spin liquid. And that happens immediately as one opens a gap, some h cubed order into the pure Kitaev spin liquid. So this phase must have another phase transition going up to infinite field where the spins are polarized, because this is a product state. So, and this is known. This is about 5% of the main coupling. So now, anchored on this point, there must be a phase boundary that somehow crosses the phase diagram. And depending on the different perturbations and so on, there are various scenarios where this phase boundary may come up here, may have different behaviors. So just to fix ideas and explore something that's discussed in the community, let's imagine a scenario where this phase diagram would look something like this phase boundary. So this has to increase this way because as we put more perturbations, we strengthen the zigzag order, so we need a higher field to suppress it. So now the question is, starting from this scenario, whether the experiments are actually in a region where you go from the zigzag order, you end up in the gapped spin liquid phase, and then you go to the quantum paramagnet, or whether you suppress the zigzag order and go straight here. Okay? And so these are some of the scenarios and ideas that are explored experimentally, and certainly there are very interesting measurements, thermal Hall and various spectroscopy is in the field region just above the critical field to try and distinguish between two scenarios and possibly even others. Okay? There's many other possibilities. So just to finish off, I showed you experiments on a range of materials. They all have dominant Kitaev interactions, which is quite remarkable given the very specific conditions that you actually need to realize this quantum frustration. But all of them have additional terms that stabilize long-range magnetic order, and these are in the form of Heisenberg, further neighbor couplings, or gamma terms, and so on. And so one question is how to suppress this long-range order and whether we'll be able to find the much sought Kitaev quantum spin liquid. And ideas that are explored experimentally are, for example, pressure tuning. You might think that via pressure you change the angles between the bonds, and those, if the exchange is very sensitive to that, then some of the ratios could change and potentially could stabilize the spin liquid. Now, an experimental challenge comes because this material, in fact, dimerizes into iridium-iridium bonds, metallic bonds. So you lose the magnetism that way. Also, I showed some scenarios in which magnetic order is suppressed in ruthenium chloride, and what kind of discussion happens there. And another aspect that I didn't mention is chemical tuning to introduce hydrogen in the layered lithium material. That leads to a much larger spacing between layers, and experimentally the magnetic order disappears. And the question is, and several experimental techniques show kind of spin liquid-like behavior, and the question is whether this is characteristic of the pure Kitaev system, parent, or what's the role of disorder introduced by the hydrogen, which can actually occupy many positions and has a very large Debye-Waller factor, so leads to some randomization of exchanges. Other issues that I'd like to point out is that so far all the Kitaev materials explored have been based on the magnetic ions iridium 4+ and ruthenium 3+. And in this case, even though the spin-orbit coupling is weaker, the local crystal environment is higher symmetry because we've lost the binding with the other layer. The layers are bonded by van der Waals, and so it allows the octahedra to expand to get closer to cubic. So this is also the reason why, this is the reason why this still satisfies this J effective a half, even though spin-orbit coupling is reduced. And one question is whether these are the only cases, or potentially there are other materials. And certainly, it's known that it's possible to get J effective a half also in other 3D ions, such as cobalt 2+, and we've seen that experimentally in some systems. Also, another issue maybe to bear in mind is that the Kitaev model is only one representative of a sort of wider class of systems with bond directional anisotropies that can stabilize quite unusual cooperative magnetic phases. And we've seen on the Honeycomb lattice how counter-rotating spiral order can come about, but also there are various predictions for triangular lattices with quite complex phase diagrams with nematic order or incommensurate phases that can be described as vortex crystals and so on. And certainly it will be interesting experimentally to look for some of this. Another possibly interesting point is that all of the materials so far, the community agrees that the Kitaev interaction is ferromagnetic. And so, however, the phase diagram of anti-ferromagnetic Kitaev, in particular the field behavior, is much richer, and so it'd certainly be very interesting to look for materials that could realize that. Right, thank you very much. Mm-hmm.
What do you call quantum power magnet, and how would you?
So this will be a phase that's continuously connected to the fully polarized without a phase transition. So for example, imagine that you start at infinite field where the moments are polarized by the field. And now, if the spin is not conserved, if there is no rotational symmetry around the field direction, there will be 0-point fluctuations building up as you reduce the field. Here, the excitations are gapped spin waves, and they're protected from decay into something else because of the gap. So what's happening is the ground state becomes dressed by 0-point quantum fluctuations, but ultimately, those can be squeezed away by increasing the field. So this is continuously connected to the ferromagnetic phase. So we still have sharp magnon excitations, but they're dressed by fluctuations. Okay, but there's still, there's no fractionalization. So this region up here, close to saturation, this is understood as a ferromagnet dressed by quantum fluctuations, but essentially qualitatively the same. So the question is whether the transition here is straight into that phase, which then quantum fluctuations are gradually quenched away, or whether this is a new phase and there's another transition. So here is a product state, and it essentially remains a product state adiabatically up to here. But this will be a topological phase that would have new properties. So this region cannot be connected continuously to the product state. You must have a phase transition, at least at 0 temperature. Sorry.
Yes, thanks for the talk. I have a very experimental question.
Mm-hmm.
You said that you used resonant X-ray scattering, and you could only use maybe 1% of the beam because otherwise your sample would get up too much. Right?
So we would get beam heating of a few Kelvin. So for example,
my actual question is,
yes?
how do you measure the temperature?
So these experiments were done in a CCR, which has a cold finger. So we have a reference temperature where the cold finger of the system is. However, we see there's an offset of a few degrees between, if we measure the order parameter, we see that the magnetic peaks disappear at this temperature, which is a bit different from the peak in heat capacity. So this temperature offset we can calibrate through thermodynamic measurements that give us a better indication of what the true temperature is. So we always expect that in the experiments we'd see a bit higher temperature because of beam heating. And if we were not to attenuate, if we reduce the attenuation, this would would change. Yeah. Actually, it would go lower. Yeah.
Well,
Okay. Right.
first thing.